I want to give a demo of a lighting technique in OpenGL graphics programming called Lambertian Diffuse lighting using face normals. It's also known as flat shading, and the reason why I want a demo of this is because I think it gives a good introduction to all the different linear algebra concepts that show up during its implementation. So if you look at the scene that I have in OpenGL, you'll see how the lighting works. I just have a pyramid that is having the light on it. It's a bit laggy, sorry about that. Let me try to get, yeah. So you can see how the light is creating a gradient across the face. So this is our vertex array, and it represents our pyramid. So you can see the three floats here. Those are all coordinates to one vertice. So you got one vertice there and another vertice. And these are relative to the model's origin. And when we end up having to move the actual model to a specific location in our scene, we're going to be transforming each of these sets with a matrix that represents the location of where we want it to be in the world. Each of these groupings represent one face of the entire pyramid. So you have four faces on the side and one face on the bottom. And here we have, for the bottom, we're going to have two triangles that make up the bottom. And the indices, which we have here, those represent how these triangles are going to be constructed. So for this demo, we're only going to be worried about the coordinates of the vertice and the normals of the vertice. And I'll go into the normals a bit later into the video. So to get a handle on this, we're going to first need to understand what it means to normalize a vector. So we have this vector here that is going to be, we're going to call it v. And when we count on the x-axis 1, 2, 3, and then on the y-axis 1, 2, that's where the vector is going to be. So first, we want to get the magnitude or the length of v. So that's what we're doing here. So obviously you guys know to get the length of it, it's Pythagorean theorem. So it's just going to be 3 squared plus 2 squared. And then we're going to get the square root of that. And yeah, that's going to give us the magnitude, which is 3.605. And then to normalize that vector, what we're going to want to do is we're going to want to take the result, the magnitude, and then we're going to want to divide that by each coordinate. So 3 divided by the magnitude and 2 divided by the magnitude. So that's going to give us the normalized vector. And you can check to see that the vector is in fact normalized by taking that result, and you can plot it just to kind of see what it looks like. And then if you want to be able to find out that it actually is a unit vector, all you have to do is take the magnitude of or length of that normalized vector. So if you plug it into the Pythagorean theorem and the vector turns out to be a length of 1, then you have successfully normalized the vector. So congratulations. Now we need to understand a little bit about the cross product. So imagine we have two vectors here, and it's in the xy dimension. And if I want to take a look at the first vector, imagine if we duplicate that and then move it slightly over here, and then duplicate the second one and move it over here. So that's going to create a parallelogram. And the reason that we need that is that's essentially called the determinant. So the determinant is the area that is created by the parallelogram. So we're going to need specifically the area because the area is going to tell us the length of the third vector that we're getting as the cross product. So in this little diagram here, we're going to have a third dimension in the z-axis. And then the third vector is going to be pointing towards z based on this example that we have. And it's going to be perpendicular to the face that parallelogram creates. And it's going to be as long as the number that the area gives us. And an important thing to know is that when we're trying to compute the cross product, it's non-commutative. So what that means is that the order matters on when you do the calculation, because One order is going to give you the cross product z pointing in one direction of z, and then it's going to give you the cross product of z pointing in the other direction if you were to swap the sign. So the order matters essentially. So now that we have cross product and normalization in our toolbox, we can take another look at our vertex pyramid in OpenGL. Now, admittedly, it's hard to represent a 3D grid in 2 dimensions here, just on a whiteboard, but I tried to draw it as best as I can to represent a 3D object. So this little plane here is just going to represent one of the faces of our pyramid. And you can kind of imagine that here's the tip of the pyramid, and then this is like one of the side faces. So you can kind of fill in the blanks of what that kind of looks like as a full pyramid. But we're just looking at this snapshot of just one of the side faces. And originally, in our examples before with doing vector normalization and even the cross product, we were working from the origin. But here, we're going to have to be a bit creative because the origin is actually going to be one of the vertices. So we're just going to choose vertice 1 as our origin. And this is really, we're just trying to find displacement. That's what we're doing when we're working from origin 0 anyways. We're just trying to find the displacement to be able to calculate the cross product. So if you take vertice 1 and you want to find the edge of what it's connecting to for vertice 2, all you have to do is take vertice 2 and minus vertice 1. And that's going to give us the edge of that connection. And what that's essentially saying is from vertice 1, all we have to do is move -1 down the z-axis, and we're going to arrive at vertice 2. So that's why it's displacement. And then to find the edge from vertice 1 to vertice 3, we're going to do the same thing. We're going to take vertice 3 and minus vertice 1. And then that's going to give us that edge here. And that's going to say from vertice 1, all we have to do is move 0.5 along x, and then 0.8 along y, and then -0.5 along z. And then that's going to make us arrive at v3. So originally, or in the last little experiment that we did with cross product, we were trying to find the determinant, but we don't really need to do that if we're actually going to find the cross product, because it's going to give us a coordinate that is the vector that belongs to that. Well, it is the cross product, but it's going to have the length in there. So we don't really need to compute the determinant. That was just me kind of explaining why the determinant relates to the length of the vector. So this is the actual computation of finding the cross product from those 2 edges that we have. So all we have to do is we just have to align it in this kind of matrix here, and or pseudo matrix. It's not really a matrix, but so like if we're finding I, all we have to do is cross out all of the things that I is touching, and then we just have to take those terms, and then we're just going to plot those numbers here for I, and then similarly for J, all we're going to have to do is we're just going to have to cross out all of the columns and rows that it's touching, and then that gives us these terms here, and then that's what we plot there. And then lastly, for K, we just block out these, and then that's going to give us the last terms for K. And it's computed in that checkered little form that you've seen before, obviously. So it's plus, minus, plus. And then, so in order to get to the next calculation here, all we're doing is we're multiplying in a kind of cross way, as you can see there, and then minusing it by the other cross way. So that's where you can see 0.8 multiplied by -1 and so on. So we plug that in, and yeah, that's going to give us the vector for the cross product. So this is actually going to be what we call the face normal. And so if you take a look at our vertex array in OpenGL, you can see that face that we just outlined. We can see that the normal that we got, which was the result from that calculation we did, is exactly the same for each vertice that we have in that face. So we can say that the normal is going to be the same for the whole face because we have 3 vertices on the face, and each normal is going to be that same cross product. Now, if we take a look at the code, when we call GL draw elements, the GPU is going to process the pyramids mesh. And if we look at the shader, the vertex shader, what's going to happen is that it's going to read every vertice, and it's going to be able to find the position as well as the normal associated with that vertex. And so it's going to find the position of where it is in the world for each vertex, and it's also going to calculate a variable called current position. Now, in the vertex shader, that current position is just going to represent the position of the vertices that are associated with the triangle. And the reason why it knows those groupings is because of the indices. And you'll notice that these exports, you see the out for normal and the out for current position. So it's going to take those normals that are associated with the vertex and the current position, which represents where that vertex is, and it's going to export them to the fragment shader, and the fragment shader is responsible for coloring the actual pixels that are in the boundary of that grouping of vertices to create a triangle. The reason for exporting normal and current position to the fragment shader is for a process called interpolation. So what's going to happen is that before in the vertex shader, we only had the current position for each vertice that was part of a face, as well as the normals. But when we send it to the fragment shader, it's going to essentially estimate for every pixel that are in the vicinity of that face. So for whatever normal and current position that belongs to that face with all of the vertices involved, it's going to make an estimate for every single pixel in that face to say what the current position of that pixel is and what the current position of the other pixel is based on, as I said, the border. And so the normals are going to be the same for the whole face. That's why it's called face normals, because all of the normals are the same for each face, and that's what creates the flat shading. But for the current position, that's going to be slightly different based on where it's where each pixel is being estimated from on that face. And that's going to be very important because that's going to determine the diffuseness and the brightness of the light that we are demoing here. So in order to understand that diffuse gradient lighting that gets casted onto the pyramid, we're going to need to learn something called the dot product. And the dot product is going to be very essential for understanding how this works. And it's also going to show us why the vectors need to be normalized before we get the dot product. So I'm actually going to show both of those things to you right now. So we have this little X and Y grid here with the 2 vectors. So A is pointing straight up at 10 in the Y direction, and then B is at -2 and 4. So to find the dot product, all you have to do is A dot B, and that's literally just taking the X terms of each of them and then multiplying them together, and taking the Y terms of each of them and multiplying them together and then adding them. And that gives you 40. So what I want to show here is that there's another way of getting the dot product, and that's actually finding the shadow that B casts onto A. Because essentially what we're trying to find is by how much is B pointing in the direction of A. So when we have that shadow cast, we can see the shadow length. So we can see, how much of this shadow is on A. So we have that shadow length, And then all we have to do is multiply that shadow length by the whole length of A. And so we have the little equation here. So that's the magnitude of B times the cosine of the angle, which is that shadow length. And then we multiply that by the magnitude of A. So the reason why I want to show this is because we're gonna take that little scene or system we have there, and then we're going to basically put it down here, and we're going to take the B vector, and instead of having it at -2 and 4, we're going to have it at -5 and 4. So it just moved three spots in the X direction, and it's still in the same spot in the Y direction. So it's a longer vector. It has a different angle, and but we can see that when we take the shadow cast here, it's actually casting the exact same shadow length onto A. So that means that when we find the dot product for this one, even though it's a different angle and a longer vector, the dot product ends up being the exact same as the other one that we had there. So this is the reason why normalizing it is so important, because if we take those two and kind of compare them in this, so we have the old B and the new one here, so we can kind of see like how far along they go, and we can see that they're longer than each other. So if we take those and normalize them so they all have a length of 1, we can compare that shadow cast to the normalized A, and we can see that that shadow cast is actually going to be different. So the old one is casting higher than the new one. So we can say here that because we normalize them, they're actually going to be different dot products. And it makes sense because if you plug the normalized vectors into the equation right here, you'll notice that you no longer have the length or magnitude compensating for the dot product. So what I mean by that is, when you have it normalized, the length of B and the length of A are both going to be 1. So now you're just having to worry about the cosine of the angle. So the dot product is only giving you the cosine of the angle when they're normalized, instead of that mixed in with the magnitude or length of the vectors. So if we take that exact same mental model and apply it to our OpenGL Lambertian diffuse lighting with face normals, you can see the exact same pattern showing up here. In this picture, I have basically I have one of the faces, and then we kind of just took a slice of them just to see all of the pixels going along in one row. So we have pixel, 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 pixel here. The little line going all the way up is the face normal that we've been talking about. And if you imagine that the direction from the pixel to the actual light, if we drew just a line instead of having it normalized, then you can see that we're going to have that same compensation in length. So it's going to be compensating in length for each further away vertice. And then if we had this face normal going all the way up here, and we casted that shadow, we would see that the shadow is the same for each pixel. So when we normalize it here, and then it's got a unit length of 1, you can see that as we move further down the row of these pixels, you can see that that cast shadow is getting smaller and smaller, because you can actually see the angle changing like that. So you can actually see that, yeah, the dot product here is going to be different from the dot product here, and then it's going to be lower as you go down. So that's exactly why we're trying to normalize it in our lighting, to have that gradient of brightness on one pixel that's close to the light, and then dimmer as we go further down. In the fragment shader, you're going to see this pattern taking place here, and it's going to happen pixel by pixel. So we had the face normal, and that was just the cross product. We actually didn't normalize that yet, so we're going to normalize that now. And then we have the current position of each pixel that we're going to be doing this to, and we have the fixed light position because that stays the same. So we're just going to be subtracting the current position from the light position. So current position of each pixel, remember. And then we're going to normalize that, and that's going to give us our light direction for each pixel. And then all we got to do is what we went over, is getting the dot product between the face normal and the light direction, both normalized, and that's going to give us the diffusion for each pixel. So all we do after that is we just multiply that by the light color and the actual texture, and the result is what I am showing here. So we have the light here, and we can see that it's brightest where it's closest to the face, and then as it goes further away, like I showed with those pixels, it gets dimmer because it's calculating a different a smaller dot product based on just the cosine of the angle since they were normalized. So yeah, that's the whole Lambertian diffuse lighting with face normals. So I hope you guys appreciated that.